Hi, everyone. Thanks for joining us. This is the pathway, second of our pathway seminars for this semester, and we have a power area faculty, Dr. Anamitra Pal, speaking, and later we'll be joined by Dr. Trevor Thornton from the Physical Electronics and Photonics area. So we're going to go ahead and get started. If you have questions and you'd like to, for our faculty, please add them to the chat. We'll moderate those at the end of the presentations. So I'll hand it off to Dr. Anamitra Pal from the power area. Thanks for being here.
Thanks, Bob. Are you guys able to hear me?
Yep, sounds good.
Let me go ahead and share my screen. Let me know if you're able to see my screen in full screen mode.
Yep, it looks good now.
All right. Welcome, students. So let's get started. So this around 20 slides that I have to show today is going to give you a quick overview of the electrical power and energy systems. We call it the EPES program at ASU. So ASU's electric power and energy program is one of the largest power programs currently in the country. We have one of the most diverse groups as far as research faculty are concerned, simulation tools, experimental labs, as well as hardware and control hardware in the loop simulations are concerned. The program at ASU in the power area ranks in the top 3 in the US as far as research excellence and recognition is concerned. We have a wonderful track record with employers, as well as many of our students have later on continued into their graduate schools and even joined academia after their postgraduate from their masters and PhDs and so on. As far as employment is concerned, power area is one of the evergreen areas, as you can imagine. The reason being that everything else can be outsourced except power systems. You need power, you need electricity to do almost any other kind of work that you want to do in a first world country. And this power or the electricity that we talk about, it cannot be run remotely. You have to, the power lines have to exist, the generators have to exist, although their forms might change, but still, we still need a source of energy. And we also need a way in which we can transfer that energy from the source to the destination. So when it comes to the challenges of the environment, the climate change, extreme weather events, and so on, all of those solutions can be addressed only locally. You cannot do it from outside. So we need to have inbuilt or in-house expertise to address the challenges that we encounter. And so that's why power systems or the area of power engineering is excellent as far as employment opportunities are concerned. This is a quick overview of the faculty that we have at Arizona State University. As you can see, we are 14 of them. We have faculty doing research in diverse areas of power systems. We have folks in power electronics, Professor Ayanar, Mike as well, and Professor Chin Lei. We have folks in stability and power system controls. We have Professor Vijay Vital, who is one of the lead faculty in the area of power in the whole world, not just the US. He's a member of the National Academy of Engineering as well. Professor Jerry Hyde, he is also an National Academy of Engineering member. He's a professor emeritus at ASU. Professor Halbert has expertise in nuclear energy. As for those of you who are keeping track of this, nuclear is making a comeback. So we will see how things, it's an exciting prospect to be. We have Professor Shankar and Professor Corey Hedman. They are professors who are working on more specialized areas like markets, economics, cybersecurity. And so amongst the young faculty, we have Professor Korsand, Hedman, myself, Amar, who has joined this semester, Yang, and Professor Mangwu. We are more on the younger side. We are looking at diverse areas, including applications of machine learning, resiliency, smart grids, electric vehicle challenges, and so on. So as you can see, we have a diverse mix of expertise, as well as in terms of the type of proposals that we can target or the research areas that we will get into. we have a lot of combined experience that we can share with our students. As far as the courses are concerned, for those of you, some of you may already have been taking EEE 360 this semester, or if not, they're planning to take it next semester. EEE 360 is the introductory course to this entire domain. And I'm actually teaching EEE 360 this semester. So if you're in the in-person session, you should be able to, you already know me then. This EEE 360 introduces you to 6 other courses at the senior level. 460 is nuclear power, 463 power plants, 470 is power devices, 471 is power system analysis, 472 is power electronics, and 473 electrical machinery. I'll give you a quick overview of what these courses are all about, and then, in the next few slides, but then we'll go from there. And as always, if you have any questions, feel free to put in the chat, as Bob mentioned. We also have a senior design projects which go with it, which is the 488, 489. All the other courses, the first 360 and the first 5 470, 400 level courses, they are offered in both internet and hybrid modes, in person as well as hybrid modes. As far as the requirements for the concentration of EPES goes, you have to take EEE 360 energy systems and power electronics. That's the introductory course. It's a 4-credit course. In addition to that, you need to have 9 hours of electrical engineering technical electives in the form of these 460 and 470 level 46X and 47X level courses. You can also take one of these special topics courses such as solar energy 498, as well as the Capstone senior design project in the form of 488 or 489 under one of the faculty who you saw a couple of slides before. So that's how we go about for this concentration. To little get more details about what we do in these technical electives, essentially we have 3 different subdivisions in power systems. We have the generation side where you're concerned with generating power. Then comes the transmission and distribution side, which is focused on transmitting that power from the generator to the consumers. And then comes the electricity utilization side, where we are trying to see how well we are able to use the power that is given to us efficiently, effectively, in an economical manner, and so on. So that's how we try to split the application areas and electives as well. So when it comes to power generation, we are looking at how power plants operate, and we focus on not only the classical forms of power plants like coal and nuclear and so on, but also on the more modern trends as far as renewable generation, distributed generations are concerned. When it comes to transmission and distribution, we are looking at power lines, the high voltage engineering. When it comes to protection of the power system, like isolation of the fault as quickly as possible. Here we are looking at removing a faulty part of the system, the healthy part of the system within milliseconds, which is like 10 to the power minus 3 seconds. So even before I finish saying this sentence, the power system has done whatever it needs to do. That fast of a control is what we're talking about. So we need to be very robust and very resilient as far as transmission and distribution are concerned. And finally, in the electrical utilization side, we're talking at the consumer end. So we are looking at the devices that are powered through the power that we receive, how to use it effectively. We are talking about different types of machines. We're talking about electric vehicles. Also, a little bit of control is involved, and so on. So there are examples of subsystems where all of these 3 entities are also present. Yeah. So there are also subsystems, as you can think of, where all of these 3 entities are present, although they may look like that is a single entity. For instance, if you think of a ship has its own generation. Maybe if it is in the form of nuclear power, there can be a small modular reactor present inside the ship, you can power it. There's obviously a distribution of power because the entire cabin has to be lighted and so on. And then there's utilization of power in order to make sure that this power is used in the right way and so on. So, there are different subsystems, which we call them even mobile power systems, which are also coming under the area of electric power and energy systems. Renewable energy is one of the biggest challenges that we are currently encountering as far as modern power systems is concerned. As you can see from the pie chart on the top right, the percentage of coal and even natural gas, they are decreasing every year. And the portion associated with renewables, which also includes hydro, is increasing considerably. Now, keep in mind the fact that we are not building too many new hydropower plants because we are limited by locations of the rivers, lakes, dams, and so on. So most of the increase in renewable generation is currently happening because of solar and wind. And some examples are shown on the bottom left, where we talk about offshore wind farms. We can have onshore as well. We can have solar panels in the parking lots, solar farms as well, and so on. So, there are different ways in which we are able to use wind power and solar energy in order to power our grid. And those are some of the things that you will be exposed to in these 400 level courses. So what are these courses all about? So EEE 463 electric power plants, it talks about generation of electric power. So from fossil, nuclear, as well as renewables. We look at both cogeneration as well as combined cycle power plants, which is a combination of gas and coal, for instance. We also look at the different types of cycles that go through it, the Rankine cycle, Brayton cycle, and so on. You'll be exposed to those concepts. We'll look at the economics of the operation, and we'll also look at their design. And finally, we also talk a little bit about energy storage. 460 is nuclear power engineering, and there we're talking about radioactive decay, radiation interactions. How does nuclear, in a nuclear power plant, how do you actually convert the power from fission or fusion into electricity? How is it generated? What kind of formulas or equations control this operation? And we'll also talk about different types of events that have happened in the past, the 3 Mile Island incident, the Chernobyl, and so on. So all of these are covered in EEE 460. Remember, this is one area which impacts everyone else. When there is a blackout, it doesn't matter what caused the blackout, whether it was a protection failure, whether it was a control failure, whether it was a monitoring failure. At the end of the day, it is the social infrastructure, the financial infrastructure, the transportation infrastructure, which gets impacted heavily. So power, or the electrical power infrastructure, is a backbone of all other infrastructures that you can think of. That's why it's an interesting and important area to participate in, because this is not all theory. You have to actually make things work and ensure that these things work, not just in theory, but also in practice. And that's where this becomes such an interesting and important area to look into. As far as transmission and distribution are concerned, we have this topic of 470, which talks about power devices. We are looking at circuit breakers, relays, current and voltage transformers. So they're called transducers because they are more from the measurements perspective. We're looking at different types of protection systems against over voltages, lightning strikes. We're talking about surge arresters and so on, how to coordinate the protection system, the insulation, and so on. All those interesting topics are covered in 470. 471 is power system analysis. And in my mind, it is one of the most direct courses following EEE 360, because some of the concepts that we are given as an input for the EEE 360 problems that we encounter in EEE 360 will actually go deeper into them as to how those problems came about. So we'll look at, for instance, we are given a transmission line and their parameters were given in EEE 360. In 471, you will actually derive how those parameters were obtained. We'll look at different types of ways of solving problems. We'll talk about symmetrical components as one way to do fault analysis, short circuits, power flow analysis. We'll also get into a little bit of stability control as well as economics for the power system. The modern power system has now become closely integrated with power electronics. The modern power system cannot exist without power electronics, and many times we actually call it electronically controlled electrical system. And power electronics, as you can imagine, it ranges from the Google data center all the way to smart lightings that you can imagine in the cities, all the way to the equipments, the appliances that you have in your homes, to the electric vehicles which you or your neighbor may be driving, and so on. So all of this is possible through the advances being made in power electronics devices when it comes to DC-DC, AC-DC, DC-AC, converters, as well as semiconductor devices. So as far as power electronics are concerned, this is where they are mostly focused on the utilization side, where we are talking about 472, which talks about power electronics and power management. We're looking at the fundamentals, equations, of the principles that govern power electronics, how to design better or more efficient converters. Plex is a software that you use for simulation purposes for power electronics, and we look at modern applications of power electronics in renewable generation interface, electric vehicles, and so on. 473 is electrical machinery, and literally, as the name suggests, you'll be working with machines. You'll be looking at DC machines, brushless DC, induction machines, synchronous machines, permanent magnet, and both conventional as well as permanent magnet synchronous machines. How do they work? We'll also have a little bit of power electronics embedded inside machines in the form of electric drives to ensure that the power system, the equipments, they function as expected when it comes to automation, wind generators, and electric vehicles as well. So all of this, we are looking at it in the cohesive, coherent manner, that once you take these courses, you'll have a holistic view of what the electric power and energy systems is all about. We also have quite a few senior design projects which we encourage, and we are looking always for good topics to work on. These are some of the projects that have been completed in the past year. Low cost 1 kilowatt power conversion system for off-grid underserved areas. As you can see, there are very practical problems that we are targeting. Cryptocurrency, solar farm integration with ERCOT. ERCOT is a utility for Texas, the Electric Reliability Corporation of Texas. One project which I led was a portable rechargeable emergency power supply, where we were looking at ways in which we could continue give power for more than 24 hours, even in absence of control or connection with the grid. We're talking about DER management. This Solar Energy District Cup is very interesting, and I believe ASU was even runner-up this year. So hopefully with you guys next year, maybe we will win it. And the link is at the bottom right. This is a competition across the whole of US. So we would definitely want our students to shine in this particular enterprise. We looked at grid integration, and you can actually, even from this slide itself, you can see the diversity of the projects, right from cryptocurrency and solar farm integration. We talk about rechargeable supply. We're talking about DER management. We're talking about even self-powered GPS pet tracking device, which may not seem directly related with the power grid itself. But remember, at the end of the day, we are looking at self-powered systems. That also comes under power system in some respect. And finally, we have mini washers for studio apartments and so on. So there's a lot of diversity, there's a lot of interest, and we're always looking for good students to work with. Currently, the power system, as you may all know, is undergoing a paradigm shift as we move from centralized generation, where generation was far away at a big power plant located, in the middle of nowhere, to a distributed energy resource where almost in our neighborhood, we'll have a large number of small units capable of producing power. These are primarily inverter-based resources which convert DC into AC, and the challenges associated with them include bidirectional flow of power, because traditionally the power was designed from generation via transmission into the distribution and utilization. However, if you are putting power in the distribution side, now there is bidirectional flow of power, so which may cause issues with controls and protection and so on. The power electronic control itself can be challenging, as well as the modern challenges of cybersecurity. Interestingly, one of my students actually did a cybersecurity project and won a best paper award at a conference last year. So, there are different areas that our professors and students in the power area, they work on, and they generate a lot of interest. There's a lot of value, and people look up to our students as well once they graduate and move out into the industry. We're looking at new technologies for renewable generation integration, new energy companies, cybersecurity solutions, and so on. And last but not the least, we also have a large number of research centers at ASU. So as some of you may know already, PSERC, which is Power Systems Engineering Research Center, is a consortium of 13 universities and 36 industries, and ASU is the lead university of PSERC. There are 3 different stems, which we call them inside the PSERC domain. There's the markets stem, there's the T&D stem, and then the power systems stem. And we have a lot of researchers which collaborate and work together. There are a lot of industry support. And through these projects, our students are exposed to the industry, and the industry become aware of our students. So there is a mutual benefit. It's a win-win solution, because the students actually work on problems that are relevant to the industry, and the industry in turn know our students, and they hire them so that it becomes a future long-term commitment once they join, and so on. A more recent one is the EVSTS, which is the Efficient Vehicle and Sustainable Transportation Systems. It is an NSF, which is the National Science Foundation funded IUCRC. We call it Industry, University, Cooperative Research Center. It's a consortium of 4 universities with about 20 industry partners, and we are looking at innovative technologies for efficient and sustainable ground transportation systems, vehicles, and so on. So that's some of the areas that, the large research centers that ASU is leading as part of this program. These are some pictures of our labs. This is our laboratories. The picture from on the right is the power electronics lab, which is led by Professor Ayanar. As you can see, we do electronic control of the power system. We also have the power simulation system simulation lab, as well as the instrumentation lab. This picture actually shows my lab on the top right. I am an expert in synchrophasor technology, and I look for different applications of synchrophasor measurements in the power systems using data analytics and machine learning. The 2 students that you see over here actually took EEE 360 with me, and then they continued to do a master's as well. And the lab below is that for machine learning in power systems, and we work closely together to ensure that we are up to date with the modern challenges of the power system. And in some sense, we are actually even going beyond that and trying to solve the problems that will occur in the future. So we always have an eye towards the future, as we call it. So I think that's all I had for today. And I believe we are like, 9 minutes at 10:21. So I'll be ready to take any questions that you may have.
Yeah, thanks very much for sharing. So I have a couple of, this would be a great time if you have questions for Dr. Pal about the power area, or even for the advisors in the room about where to go. One question about the slides being available. Yes, we will also make the recording of the presentation available on the website, and we'll put that in the chat in just a moment, so you'll get the slides. While we're waiting, it's a common question from many of the students to ask in general about how undergraduates might be involved in research, and so I want to encourage everybody to speak individually with faculty if you're interested in the power area, just specifically, or maybe studying it later to getting more involved in this. It's a very good idea to contact faculty in the power area and ask questions, meet them during their office hours and think about that. Dr. Powell, we have a question from Aaron, it looks like.
Maybe I'll just add up one thing is that there's always this option of FURI, the Fulton Undergraduate Research Initiative. So we are always looking to support students and working with undergraduate students as far as FURI is concerned. And as Bob mentioned, feel free to reach out to us with emails of, you can drop by during our office hours. I mean, since you may not know our office hours, just drop by our office. And if we are there, we'll definitely let you in and talk and so on. We always are looking forward to emails as well, interesting ideas that you may have or things that you may want to work with. And the way I think we go about this is we polish ideas. And then, whenever you give an idea, we give some comments, and then we, iterate back and forth. And then the idea develops into something novel and new and interesting. That's how I feel it goes. Yeah.
Thank you. Yeah, and there's a question from Aaron. Do any of the labs support 3-phase motor design?
They do. As a matter of fact, the EEE 360 has a lab dedicated to it. So when you take EEE 360, you will be exposed to 3-phase circuits, and we'll talk about transformers, induction motors, synchronous machines, and in the labs, especially if you're in the in-person session, you will be actually doing the experiments with those hardware components.
Great. And then Julio is asking about a senior design course structured for online. So in general, when you get to EEE 488 Senior Design 1 Capstone, you have a chance to form a team, and we do not require online students only to work with online students. Often it happens that way, but sometimes there are blended teams. And generally, and just to the key theme of power, if you're into power concentration as your major, you should do a capstone project related to the power area, and the way that's done is by having a power area faculty mentor it, or having the approval of the power area chair, which is Dr. Raja Ayanar. But in general, about senior design courses structured for online, we don't really do them differently. Online students just have to interact a little bit, at a distance. So they might have things shipped to them. They might have different roles based on who has access to what. Sometimes it actually works out great when there's a campus-based team blended with online. So just it's good to think ahead on that, but you don't have to. There are no restrictions, I should say, for online. And then a couple more before we move to the next area. So Zachary is asking, do any of the 400 level courses cover reliability standards and compliance for utilities?
That's a great question. So as far as compliance with utilities are concerned, many of our courses are closely aligned with utilities, because after all, we are solving problems, challenges, preparing our students to work in the power industry and so on. As far as reliability is concerned, I would say 471 might be a good course to look into, because there we will have topics related to reliability in the sense of power system control, operations, and so on. But there is also courses at the graduate level which are more dedicated towards reliability and resilience and so on. So as you will see that as you take more and more courses, these topics, which may look like a simple word in itself, they end up becoming an entire course in their own right. It's just different courses have different aspects of it, but then as you go along, it becomes as you go deeper, you get more and more information about them.
Yeah, that's great. A couple more here. So Raul is asking, so we have students in the room. Obviously, we have a BSc in electrical engineering, and we have a BSc in electrical engineering that has a power concentration, which is really just a concentration of some power courses at the end of the degree. So Raul is asking, do you think getting a power and energy systems BSE would limit his opportunities for non-power career opportunities if he wanted to do something outside? I'll first, and I'll let the faculty speak to this too, but I first would start off by saying that the degree, even if it's power concentration, is still quite broad in electrical engineering, and you do get plenty of exposure. So my gut reaction is not exceptionally restrictive, but Dr. Powell, do you have any comments on that?
So I worked for a couple of years in the industry, and based on my experience, this is what I will say, that when you work in the industry, they don't ask you whether you are an electrical engineer or a mechanical engineer or an electronics engineer. They ask you whether you can solve the problem or not. If you can solve the problem, that's it. They'll acknowledge you and they'll support you. So at the end of the day, we have to be problem solvers. So as far as degrees are concerned, and as Bob mentioned very correctly, although we're calling it the power concentration, you can see that there are a lot of areas within power systems where different concepts are used. We are working with people from computer science, from physics, from chemistry backgrounds, from data scientists, and so on. So all of these areas, all of these people from very different backgrounds are able to find topics to work on in the power systems concentration. So as a matter of fact, power is one area where you can have all of these things put into place. So I personally do not feel that having a concentration in power is going to prevent you. It may actually benefit you even if you look for non-power system jobs, but I don't believe it's going to hinder your job prospects.
Yeah, I think it's a very good question, because we do create these concentrations, and they do seem to market towards something. I would say personally, if you're the most important thing besides your degree would be professional experience, doing an internship, getting a paid internship, that sort of thing would be probably even more valuable than the concentration of your bachelor's degree in your career choice. So keep that in mind. But that's an awesome question. Thanks for sharing that. And one more question on power before we jump into the next presenter.
Mm-hmm.
So for students who major in power systems but are interested in the 4+1 program, what do you recommend their pathway be? Should focus on as they continue their studies?
That's a great question. I would suggest there are so 4+1 also includes a master's degree, so you have to take 500 level courses. And I know for a fact that some of the 500 level courses that you should be taking, maybe 577 is power system operation and planning, and 579, which is transmission and distribution. So I would say those are the common courses, but I would definitely encourage you to reach out to your academic and graduate advisors, because they can also guide you more on this. We are more, so as faculty, we are more on the technical side, but yeah, when it comes to courses which are designed to help you and so on, I guess they are the best people to give you inputs.
Yeah, Lynn, do you want to jump in real quick on that one?
Sure. So you definitely want to start off with 360 as your pathway class. And then for your technical electives, you'll want to take a look and see which 400 level classes you would be interested in. Dr. Paul mentioned several of them earlier. The 400 level classes are often the recommended prerequisites to some of our other 500 level classes. So when it comes to 4+1 planning, we have to plan backwards. At the end of your master's program, you're going to take the comprehensive exam based off of courses in your area of specialization. Dr. Powell just mentioned 2 of them. So clearly you want to take those classes and then look to see what the prerequisites are for those classes and take those classes to prepare you for them. And then double check what the prerequisite is for, those first prerequisite classes, which would definitely be 360. So starting off with 360 is the best place for you.
Yeah, in early advising, if you're curious about 4+1, is super important. So maybe email your advisor if you're interested in 4+1 early on. And then real quick before we jump into Dr. Thornton, yes, we will have the recording available and posted to the website. Should be in the chat if you scroll up a bit. So Dr. Powell, thank you very much for being here. Thanks for the great presentation, and students, we really appreciate you asking questions and engaging with us. So thanks, Dr. Powell. You're welcome to stick around and hear from Dr. Thornton, who's speaking on the physical electronics and photonics area. So Dr. Thornton, I'll go ahead and introduce you and mute myself. If you'd prefer, I can stick. I'm encouraging students to add their questions for you to chat, and that we can moderate those questions at the end. And some of them are advising related, some of them are faculty related, so we'll do it that way. But thank you, Dr. Powell, for being here. Yeah, we appreciate your time. And
Very
students, yeah, I'm going to go ahead and introduce Dr. Thornton now. So thanks for being here.
Very good. Good morning, everybody.
Good morning.
Great, 40 participants. That's wonderful. So yeah, sure. I'll pay attention to the chat. I've got some few slides here. But the first thing I want to say is, this is a fabulous time to be interested in physical electronics and photonics. And I'll get to this towards the end of the slides I'm about to present. But really the investments and the infrastructure and the job opportunities in this broad field that the media is calling semiconductors and we call physical electronics and photonics. It's a fabulous time to be getting involved in this industry for a long-term career. So let me, have you given me permission to share? Let's see, share screen. Here we go. Yes. So I'm going to load my slides, and then if I put them in presentation mode, which screen are you seeing? Are you seeing the main presentation screen, not my notes page? Bob, can you tell me?
I'm not seeing anything yet other than the participants.
Interesting. I'm sharing my screen. So, all right, well, let me get out of that. And
sometimes presentation mode's a little wonky. There we go. I can see.
So
yeah.
Is that the presentation mode, or do you see my slides in the side?
The slides. Yeah, there you go. It looks good now.
Well, very good. So it's interesting. So we just heard from Dr. Powell about power systems. And I wanted to begin with this image of a Waymo self-driving car. So there was a time when you would see fleets of these driving around the Tempe area as they trained them. And so this really represents the sort of ultimate integration of all these semiconductor systems into making this self-driving autonomous vehicle. So you heard from Dr. Powell about power systems, and of course a lot of that technology runs on specific chips that are designed to handle high powers, and this is a growth area. So I'm personally researching this, and I'll talk a little bit more about that, but semiconductors that can handle the high voltages and high currents that are present in everything from a nuclear power station to a self-driving vehicle, that's critical. These, you can see here, this dome on the top, I think this is the LiDAR radar system. And so the communications output and input communications are really pushing the boundaries of what we can do these days. And so this the self-driving car has multiple radars, multiple sensors, so optical sensors, ultrasonic sensors, optical sensors to look for pedestrians, and it's all coupled together into one sort of communication system. And of course, that's all controlled by an enormous computing power. So I've forgotten the statistic, it's pretty significant. The cost of a car these days, a large fraction of it is due to all of the electronics that go into the system. And then the final thing, feedback, the car is driving itself. And so it takes all of this input, all of this data, and uses that to then mechanically control, the speed, the direction, and how you do that in real time in a safe way, again, involves enormous amounts of computing power, sensing chips. So this represents the pinnacle of where we are today. And of course, this is where we've come from. So vacuum tubes. I don't know if any of you are audiophiles who like to get the best possible sound from there. So you can still buy audio amplifiers that are made from vacuum tubes because people argue that they have better sound quality. But you're not going to be able to build a 50 billion amplifier computer using vacuum tubes. And so this technology quickly dwindled away as soon as we developed these first integrated circuits. I saw this chip. This is part of the Smithsonian. If you go to the Smithsonian museums in Washington, D.C., this is part of their rotating exhibit. So every year or so, they rotate this first integrated circuit built by Jack Kilby and his colleagues at Texas Instruments. This was a voltage controlled oscillator, and it's several centimeters, inches in dimensions. That quickly developed into these large mainframes. So for most of you, this is all ancient history, and this is where we are today. So electric vehicles, that's driving a lot of the automotive needs for semiconductors. All our handheld devices, laptops, cell phones, iPads, tablets, we're all very familiar with this. Solar power, this has become very affordable now. I think electricity from solar power is competitive with that from fossil fuels, even with no subsidies. This is interesting, high power radio frequency integrated circuit. So you basically take an entire benchtop waveguide system and you integrate it down onto a piece of silicon. And then of course the computation required to do self-driving vehicles safely and efficiently. Now, I'm sure many of you heard of Moore's law. This is really the industry trend that has driven semiconductor manufacturing since 1970. Basically, Moore's law, it's not a fundamental law like F equals ma, but it is a sort of empirical recognition that the number of transistors on a chip doubles every 18 months or so. And so you can see that first chip from Texas Instruments, that voltage controlled oscillator, that had about half a dozen components back in late 1960s. Intel developed the first microprocessor down here with a few thousand transistors. Now we're up, look at this number. It's hard to get your head around this. 50 billion transistors on a single chip. So astonishing integration. There's no other industry quite like this in terms of volume of products that it can manufacture. And we talk about the like I said earlier, the media talks about semiconductors, and so when I teach a class, we recognize that there are different types of materials. There are metals, which are very good conductors. There are insulators like glasses that are very bad conductors, very good insulators. And then there are semiconductor materials like silicon, gallium arsenide, gallium nitride in between. So those are the materials. But when we talk about semiconductors, we're really talking about the chips themselves and the systems they go into. And in a sort of broad term, we describe these chips as having either a digital function, so a microprocessor might contain billions of transistors doing digital logic, but we also talk about analog components. And So, you know, an operational amplifier chip is a good example of an analog component. Radio frequency integrated circuit, that's a high speed RF analog component. And of course, now the trend is to integrate as much of this as possible on the same chip. So we'll have mixed signal, both analog and digital. Now, to operate these, we need to understand how semiconductor devices work. So diodes, transistors, lasers, LEDs, there's a whole range of these. And, you know, part of that is understanding, well, first, the sort of physics of how they operate, and then how you would design a device to perform a certain function, how that device is fabricated. Once you built it, you need to measure and characterize it to make it sure that it's working the way you want. And then, because it's so expensive to build your first microprocessor, we go to great lengths to model the circuits that we're designing. So we can model them so that they work almost, you know, they work practically the first time, the first pass manufacturing. And then, of course, you need to sell those chips, you need to market them, find customers, and ultimately sell them. And, you know, these last two, we've all seen this recently. These supply chain disruptions mean that, you know, cars were difficult to get hold of because the manufacturers couldn't get enough semiconductor chips to put in those cars. So, you know, how you market and sell these semiconductors is a whole field in itself. All right, so the things we focus on for our undergraduate curriculum are the device physics, circuit design. We have strong programs in circuit design, fabrication. We're very fortunate at ASU that we have state-of-the-art clean room and materials characterization facilities. And so there are some classes that I'll talk about where you can actually go into the clean room and get hands-on experience fabricating and characterizing devices. We have very strong modeling programs. So how do you simulate and integrate? How do you simulate a transistor? How do you then put that into a circuit, into a high density integrated circuit, and then measurement capabilities? So these are things that we teach in our curriculum. So these are the classes that I want to focus on. Now, all right, a secret for you. Don't tell the dean, but all my degrees are in physics. And so back 30, 40 years ago, the applied physics that we were doing 30 or 40 years ago is today's electrical engineering. So a lot of the things I did for my PhD were based on quantum mechanics applied to semiconductors. And this was very new at the time, so it was considered physics. Now, to be able to understand how a laser works or how a high-speed transistor works, you need to understand the quantum mechanics that controls how the current flows in these devices. So here we are in an electrical engineering program teaching a class that 30 years ago would have been primarily in a physics department. So quantum mechanics for engineers, fascinating. I think, you know, this wave particle duality, it's a very fascinating subject, and this is a good way to understand that as it's applied to engineering. Now, a class I'm actually teaching this semester, EEE 435, Fundamentals of Cmos and MEMS Fabrication. So Cmos is complementary metal oxide semiconductors. So that's just a generic name given to silicon chip manufacturing. MEMS, I'm sure many of you are familiar, micro electromechanical systems. So, you know, when you rotate your cell phone, it knows that the orientation of the display has changed, and so it flips the display for you. That's because inside your cell phone is a mechanical component that vibrates as you accelerate it in that rotation, and it turns that mechanical vibration into an electrical signal that knows that you're rotating it. And so now this is a huge industry. It started really, the first products were the crash bags in your car. You know, the MEMS component there, an accelerometer, recognized that you were in a life-threatening collision and would detonate an airbag all within a few milliseconds. And then it's gone from there to digital light processors. So some of the highest intensity video projectors are made from a chip that contains thousands of little micro mirrors that steer the light to generate your high definition image. And then multiple components in cell phones. So CMOS and MEMS, these are very important industries. And this is the class where we take students into the clean room and you learn the fundamentals of cleaning wafers, first health and safety in a clean room environment, that's very important. Then how you clean wafers, how you deposit material, how you etch material, and how you do photolithography to put it all together. So this is a good class for that hands-on experience. Now, to understand how the devices operate on that integrated circuit, you need a class like EEE 436, Fundamentals of Solid State Devices. So the prerequisite to this is EEE 352, Properties of Materials. So in Properties of Materials, we finish with a PN junction diode and how that might be used as a rectifier or as part of a solar cell. We then take that, so 352 is a prerequisite for 436. We then build on those ideas to learn how MOSFETs work, how metal oxide semiconductor capacitors in general, more details about diodes, bipolar transistors, maybe some of the more advanced transistors that lead on to the sort of 500 level classes. So again, 436 is an important class to understand how those transistors work. And sort of in parallel with that is optoelectronics. So the emphasis in 436 is on devices that move current around. Then 437 is a class where the emphasis is on devices that generate light, so light emitting diodes or lasers, or they detect light for optical sensors, or they propagate light through optical waveguides on an optical integrated circuit. So again, to get a solid background in this material, you need to understand how electronic devices operate, as well as how optoelectronic devices operate. And then 439 is a class that tells you how clean rooms are designed, how they are operated, and how they're maintained. So with the industry that's available in the sort of metropolitan Phoenix area and in the Southwest in general, having an understanding of how semiconductor clean rooms operate is a useful course to have on your resume. And then, of course, here in the desert, we've got ample amounts of sunshine. So we're one of the sort of national centers in solar power research and development. And so 465 is a good fundamental class explaining how we take light and turn it into electricity using a PN junction diode and all the things that go with that, right? Not just the science, but the manufacturing and economics. We have to do it at scale, so these things have to be affordable. So maybe I'll take a slight pause there. Are there any chats? Not yet. So okay, let me carry on. ASU has very strong research programs that cover a lot of these areas, and here are just some images that sort of highlight that. So leading on from the previous slide, we have a world-class solar research program. Our faculty own the world records for the highest efficiency solar cells that you can make. They study how you can optimize their design to reduce cost, and then importantly, how you build them with components that you can recycle. If a solar cell installation lasts for 20 years and you're putting in terawatts of capability, what happens 20 years from now when you have to recycle all that material? So lots of exciting programs based on solar power. I talked about optoelectronics. So one of our faculty developed a white laser. Now, this is, for those of you who know about lasers, this is a bit of a contradiction. The idea of a laser is that it emits light at just one very narrow range of frequencies. And that's important for lots of applications. But it turns out if you want to make a very bright TV, a television, well, we use LEDs that are red, green, blue at the moment, but we get to make them even brighter if we could use lasers. So a colleague of mine at here developed a way to build essentially 3 lasers on the same chip, so they emit at these different wavelengths, red, green, blue, and so when they merge together, they appear to be white. So again, very clever technique that may one day be in the television that you buy. And then all of this, wide bandgap power devices. So you heard Dr. Pal talk about power electronics. We have faculty who are building transistors from gallium nitride. So this is a device that can take very high voltages before it breaks down, and it can also support high currents. I'm interested in diamond electronics. You know, we all know that diamond is this gemstone that's a fabulous insulator, but under the right conditions, you can turn it into a semiconductor. And I didn't know this until I started working, but diamond has the highest thermal conductivity of any known material. So, you know, higher than metals like copper or silver. And so many of the limitations that we're facing is you can't make a system 100% efficient. So always some of the power you put in is converted into heat. And if you've got a high power system, you're generating lots of heat. And how do you get that heat out before the system fails? So if you could build your high power device out of diamond, you could make it probably 10 times smaller than it exists at the moment, just by the capability to be able to suck that heat out more efficiently. And then all of this is underpinned by, you know, we have state-of-the-art nanofabrication, fabrication and characterization facilities. So this is this is Carrie, our photo engineer in our clean room working with our aligner. And this is one of the tools that students who take my 435 class, they'll be using this in a few weeks. So what do engineers do in the semiconductor industry? I can't explain this in just one slide. I mean, it's everything. So what I tell my graduate students is, you know, get experience with both. You know, we talk about breadth and depth, right? So you want to have classes that go, you know, cover a broad field of things you're generally interested in, but you also want to be an expert in one area, and so that gives you the depth. And so I always recommend people to, you know, cover classes. So, you know, Dr. Powell talked about power electronics. You know, take a class that teaches you how power electronic devices are used in these high power electrical systems. Circuit design, you know, we build transistors so they can be used in circuits. So cover classes that explain how you design a circuit, you know, the modeling tools, the design of those, the optimization and the layout so they can be manufactured. Simulation and modeling is very important. It costs so much money to build a large scale chip that you can't just afford to build it and see if it works, and if it doesn't, fix it and build another one, and, you know, iterate it until you get, you know, a mask set for a state-of-the-art microprocessor costs tens of millions of dollars, just the optical mask plates you need to then start your manufacturing. So you're not going to invest $10 to $50 million in a mask set and then find, oops, oh, I made a mistake, I have to use another mask. So the way we ensure that doesn't happen is by simulating these circuits like crazy. And so we have fabulous tools that allow us to simulate and model the behavior of our circuits, so that when we come to build them, you know, we're almost guaranteed that they're going to work first time. Fabrication. How do we take a silicon wafer and turn it into a chip with 50 billion transistors? And then, you know, how do you measure and characterize those devices? So, and finally, sales and marketing. So, semiconductor engineers work across all these fields. And so, you know, there's some examples here. So energy, you know, we have First Solar and other photovoltaic manufacturing companies here in the Valley. You need to understand how the devices work so you can optimize that solar panel. And then, you know, here is a silicon chip. So if you're working for an Intel or a Micron or an ON Semiconductor, you need to understand how your semiconductor device goes into a circuit, how that's built and packaged and then ultimately sold. Optics and communication. This one here, equipment. This is an example of an extreme ultraviolet stepper. So this is a lithography tool that's used in the industry to manufacture, you know, these 7 nanometer chips. And the New York Times had an article about this a year ago and described it as the most complicated machine in the world. So the engineering that goes into something like this, and the supply chain from all the countries, all the companies and the different companies that contribute to it mean that this component is the single most important in any of these new factories. And so when we talk about semiconductors as a national resource, having the capability to work with a tool like this is critical to that. So enormous job opportunities. So this is just a list of some of the companies. So we know about the chip manufacturers, right? So the famous ones, Intel, Texas Instruments, chip manufacturers. TSMC is a big foundry that builds chips that other people design. Then we have sort of less well-known, but sort of equally important are the equipment manufacturers. I showed you that chip from that extreme ultraviolet stepper from ASML. You can't build the chips unless you've got that stepper. Applied Materials, they make a lot of the deposition and etch and tools that are used to fabricate them. And then there are companies like Agilent and Keithley who develop the electronic systems that allow you to measure your chips once they're manufactured. And then sort of in parallel with all this are the companies that provide the service capabilities that you need. So, simulation software, technical computer aided design. A lot of our students, so our students who take the device modeling classes go and work for companies like Synopsys and Silvaco, developing the next set of TCAD tools for simulating the next generation of chips. So job opportunities, I mentioned this, it's been interesting, the jobs follow the global sales. So we'll have peaks and troughs, peaks and troughs. The amazing thing that's just happened in the last few months is that the Chips for America Act was passed. So this has been, it started in committee discussions back in sort of middle of 2020, but it was finally approved and signed by the president a couple of months ago. So CHIPS, right? So this is interesting. Creating helpful incentives to produce semiconductors. What a great acronym, CHIPS. Creating helpful incentives. So those helpful incentives come to $51 billion, so billion with a B. Now, the bulk of it, 39 billion, is to encourage manufacturers like Intel and many others who have been moving their manufacturing capabilities to other countries where it's cheaper to have them built. These incentives will provide the opportunities to bring those manufacturing capabilities back to the US. And so we'll see examples of that on the next slide. But there's lots of, look at this, $11 billion for research and development. So ASU is very excited about the opportunities that will be available to us to do, very advanced R&D on the next generation of semiconductors. And then, as a result of all this discussion about incentives, Intel is building a state-of-the-art facility here in Arizona. So to build one of these chip manufacturing plants, minimum of $20 billion, right? Enormous investment. And then likewise, TSMC, Taiwanese Semiconductor Manufacturing Corporation, they're the biggest manufacturer of semiconductors, but as the name implies, most of their operations are in Taiwan. They are building a new factory here in the valley, and I was driving down I-17, driving south on I-17, sort of down the Glendale area, and if you look to the west, you can just see acres and acres of cranes, like a forest of cranes building this facility. So fabulous time to be working in semiconductor manufacturing. So of course, the question is, you're here thinking about what your technical electives will be and your senior undergraduate classes. So congratulations, you'll soon be graduating with your BS degree. You might want to think about graduate school. And I heard talk about our 4+1 program. That's a very good way to get a master's degree in just 5 years. So you had one more year after your bachelor's degree to get a master's degree. So I'm getting a lot of requests from industry folks I know for students who are graduating with their master's degree, students who are graduating with their PhDs, but also bachelor's degrees and technicians from community colleges. So it's really up to what your plans are. A bachelor's degree is a very good place. Having a bachelor's degree is a very good place to be at the moment. Master's degree maybe gives you a little bit more flexibility in picking and choosing who you work for. PhD it's extremely specialized. The only reason you should do a PhD is because you're extremely interested in the subject and you just want to learn as much as you can. The advantage of having a PhD and working in industry is that I showed you the graph of the sales matching the jobs following the sales. So when we go into a decline, companies will let people go. They never let their PhDs go. They've invested so much time and energy recruiting and nurturing these people that the PhDs just move on to a different aspect of the industry. So I think I'm almost finished there. Yep. So why don't I stop, and Bob, you can take over and see if there are any questions. I'll start sharing my screen so I can see everybody's.
Yeah, thanks again
Zoom
very
windows.
much. We did have a couple of questions. One student is asking if we are doing any research or any research being done in the field of graphene.
Oh yeah, lots of programs. And now graphene's moved on from graphene. We have these two-dimensional materials, so molybdenum silicide, silicene, germane. So there's a whole raft of two-dimensional materials that our faculty are working on. And if you Google 2D materials in ASU, you'll see a lot of those things.
Yeah, thank you. And then Jason is asking, so an undergraduate with a kind of the pathway focus in semiconductor solid state flow well into a 4+1 in the computer engineering master's program. So what are your thoughts on people studying kind of this pathway as an undergraduate and then being a computer engineering program?
Yeah, so I'm not the best person to answer that, except one thing I can say is that a lot of the future of computers engineering, people talk about this, quantum computing and artificial intelligence with specific chips that are designed to do machine learning. And so there is a sort of a niche of computer engineering that's looking at how do we build chips that will allow us to do quantum computing? How will we build chips that allow us to optimize machine learning and artificial intelligence? So at that level, there's a very important interface between people who understand semiconductors and people who understand computer engineering. If you're more interested in a traditional computer engineering degree, then and I'm not sure I know what that really is, but if it's a lot of software and coding, then you may not need to know the principles of how a gallium nitride power transistor works, but the future is definitely going to be this artificial intelligence and quantum computing.
Yeah, Jason, I would strongly recommend too, in a couple of weeks when we have our graduate professional pathways, Dr. Martin Reislein, who's an EE faculty member who's also the program chair for the computer engineering program. You should definitely join that one and hear what he has to say and ask him directly. I think you'd get a lot of, Dr. Reislein's very, he'd explain this very well. Lynn, do you have anything to add to that?
I was also just going to mention the quantum computing information. Students, I don't think you realize that our graduate programs are ever evolving. And as we have more faculty teaching different classes with different backgrounds, we are adding more and more classes to the graduate curriculum for required classes and electives. So quantum computing is becoming more and more popular within the computer engineering field. And if you are interested in quantum computing, you might want to talk to two of our newest faculty, Dr. Arndt and Dr. Sinha.
Yeah, thanks. We are pretty much at about time, so I don't want to keep everybody too long. Yeah, Jason, thanks for the thanks. But everybody, yeah, oh, real quick, let's try to do this one real quick for Alejandro. So do you have any advice on how to gain experience in this field? I'm a junior and I feel like I have not done enough outside of school. Alejandro, first of all, I would encourage looking into internships on your through the Career Center. So talk to them. But Dr. Thornton, do you have anything to add to that?
Yes, there is a program that's widely recognized now, and it's I think it started with the National Science Foundation, but a number of agencies do it. So research experience for undergraduates. So the REU program, research experience for undergraduates. These are often, they can either be a summer program. I organized one for about 9 weeks in the summer, or it can be a sort of a 12-month program throughout the school year. But basically, it connects you with a faculty member in a work on a research project that you're both interested in. It provides some stipends for you, as well as the cost of the program itself. So yeah, look for REU opportunities that you might be able to apply for. And I'm thinking, typically those would be the end of the year for the following summer. So lots of opportunities.
Thanks. Yeah, so I'm gonna go ahead and let's go ahead and end it just because we're near the end of time here. So thanks, Dr. Thornton, for being here. That was an awesome presentation.
Yes.
Students, thanks for being here. These were great questions, and we really appreciate you engaging with us on these presentations. Come back next week. Come back all weeks. So thanks very much.
Thanks, everybody. Bye-bye.
Thank you.